Nothing like a brisk walk on a winter day to get re-energized. Let me know if you think you know where we are. Back to the problem set. Number 28, we have a BF3 molecule. We're going to combine that with a fluoride ion and get the tetrafluoroborate ion. Let's start by drawing the lowest structure for the boron trifluoride molecule. Boron contributes 3 valence electrons. Fluorine contributes 7 each, but there are 3 of them. 21 plus 3 is going to give us 24 valence electrons to work with. Put boron in the center because fluorine is the most electronegative element. That is not going to go in the center. Let's surround it with the 3 fluorines. Let's connect the terminal atoms to the central atom. Those are 3 bonding pairs. That's going to eat up 6 of our 24 electrons. So we're down to 18. We're going to put all 18 on the fluorines to give the terminal atoms the octet. And there's your lowest structure for boron trifluoride. And you might be like, well, why didn't we take a lone pair and make a double bond out of that? And if you do that, then you'll get all wacky formal charges. And boron is a classic example of an exception. Boron molecules are oftentimes exceptions to the octet rule. And they're happy that way. They're very small molecules. They're good with just the 6 valence electrons they have. All right, we're going to combine that with the fluoride ion. Is an ion, it's a halogen. So recall that their most stable ion is going to be 1 negative because they have 1 spot left, or they got 1 spot to fill. And they're going to do that, and this whole thing is going to be a 1 negative charge. Remove these brackets for a second. Now notice when they combine, boron doesn't have any more valence electrons to make a bond, but fluorine comes in with 4 lone pairs. So what you have in this case is a coordinate covalent bond, which is where a lone pair, 2 electrons from one of the atoms, is contributed to make that covalent bond. So let's see what that looks like. So now we got boron in the center again, and this time we'll surround it with 4 fluorines. Now sometimes you'll see an arrow indicating that that pair of electrons originated from the fluorine. So here is the lowest structure for BF4 minus. Now let's compare the geometry between the BF3 and the BF4 minus. So notice the central, the boron in BF3 has 3 regions of electron density. 1, 2, 3. They're all bonded. There are no lone pairs. So when you have 3 regions of electron density and there are no lone pairs, then that geometry is going to be trigonal planar. It's a triangle all on the same plane. So that means the bond angle here is 120 degrees. Now, when you add another fluorine to that central carbon, like we added here, then that's going to create more repulsion to the 3 that were already there. So you can imagine that the shape is also going to change. So now that we have 4 regions of electron density, or 4 electron regions, and there are no lone pairs, so that molecule is tetrahedral in shape. With bond angles of 109.5. And you might be like, well, they look perpendicular to me, Mr. Lee. Well, that's because I have a flat screen and these are really three-dimensional. So I'll try to draw this more three-dimensionally. There's your central boron. That one's up there, straight up there. This might try to do that 109. Does that look? So this one is coming out at you. So I'll draw a little bit bigger right through the screen, and then there's another one kind of going back there behind the screen. So I'll draw that one a little bit smaller. And these are right on the screen. There we go. Let's get the